Okay, I think maybe we'll go ahead and get started in just a minute here. We're broadcasting this to a couple of other facilities online, so hopefully we won't have any glitches, but if we do, I apologize. It's the first time we've tried to do this through Google+. So anyway, hopefully we won't. So we've done some testing and it seemed to work out okay. Okay, well, thanks to everybody for coming on spring break week. Yeah, it was this rescheduling of the talk was based on some weather we had a couple of weeks ago. There were a bunch of schools closed for who knows what reason, a little bit of ice and snow on the road, so we figured maybe we'd go ahead and reschedule. And then we found out we'd rescheduled on spring break week, but we figured we'd go ahead and get these started. So this is going to be the first, actually, of a number of informational seminars that we're going to start giving in the GTAC. Prior to this, most of the talks that we were given were more about what the GTAC does and the different technologies and so on and so forth. And we've clearly been getting, especially with some of the newer technologies that we utilize and offer to folks here in the university as well as outside the university, we started to get a lot of the same questions over and over again from a lot of investigators. And RNA-Seq being one of the newer technologies out there, comparatively speaking, to things like microarrays and genomic sequencing and so on and so forth, it has generated a lot of questions from folks. And we thought it would probably be a good time to start having a few of these informational seminars where we pick on a technology like this and really start to go in a little bit more detail for folks so they can really understand how to apply it to their particular experiments and scientific needs. So just a little bit of background on this particular, actually I should back up just a second. So the next one that we'll be doing will probably be on high throughput PCR, and the one after that is going to be linked to this one. So today I'm going to go into a little bit of detail on RNA-Seq gene expression analysis on the analytics downstream of the sequencing, but we're going to have a talk that is solely dedicated to expression analysis, microarrays, RNA-Seq, etc., and go into a lot of the details of analysis and interpretation of these high-throughput transcriptional technologies. So today, again, this is really focused around RNA-Seq from sort of A to Z, really, at least as well as we can do within an hour. So we're going to talk a little bit about the basics. Going to talk a lot about selecting an approach to do this, the library preparation, and the sequencing considerations. And then we're also going to get a little bit into the analysis techniques as well as comparing RNA-Seq to microarray. This is a question we get all the time from folks. What's the best thing to use for my particular application? Reviewers are badgering me that we should be using RNA-Seq for everything. Is that really what I should be doing, etc.? So we're going to try to address some of those questions. So this is really just an overview slide to sort of get us all oriented into the same place to talk about some of the next few slides. So the process of generating RNA-Seq is really not much different from, let me get my mouse to work here. It's not really that much different from something like a microarray. You're going to start from cells or tissue of some sort. You're going to isolate your RNA. You're going to basically look at the QC of the RNA, and this is critical because what you do next is going to be very dependent on what that QC looks like. Then you're going to do your library prep where you tag these things and barcode them, amplify them, etc., throw them on a sequencer, do your sequence alignment, do your analysis, and then finally do your interpretation. Today we're not going to get too much into the analysis and interpretation, a little bit into the analysis, but the interpretation will really be for another discussion. So the biggest first question we get from folks is, what should I be using? There's a plethora of different RNA-Seq preparation protocols out there. And this is really the first question we get from most folks. What should I be using? Should if I'm looking for messenger RNA and I'm really interested in overall gene expression profiles, should I be using ribosomal depletion? Should I be doing poly-A selection? Should I be using an amplification approach, etc.? So a lot of this boils down to what I mentioned just a minute ago, and that is understanding the quality of your RNA, what it looks like, what's in there, etc. So up in the upper left corner is a bioanalyzer trace of what is some very good, clean, intact RNA. This kind of RNA can be put through just about any protocol you want. The RIN number, RNA integrity number, is going to be very high. As you go to the one below that, this RNA is partially degraded. You can see that from a couple of features. One, the 28S peak is getting smaller, and you're starting to see this buildup of material, of shorter material within the trace. And then finally, at the bottom of this is very degraded RNA. Okay, this is stuff that might come from an FFPE sample or some other scenario where the RNA was highly, highly degraded. And the types of protocols that you can use with this kind of RNA are very limited. There are really only a couple of them that can work with this, and we'll go into some of those in just a bit. One of the other features that we run into with RNA quite often is DNA contamination. So it's not unusual for folks in doing their RNA isolation to get some genomic contamination in there. In and of itself, that's not a big problem. But with some of the preparation protocols, we believe that DNA or genomic contamination can actually add background in there that will shrink your differential expressions, basically add sort of a non-specific background, if you will. So we really recommend cleaning this up. This is an example of some modest DNA contamination in the upper right. Just below that is heavy DNA contamination, and below that is bacterial contamination. You can tell when you've got bacterial contamination because you start picking up additional ribosomal peaks. Okay, I've shown 6 examples here. I can tell you that we see probably at least twice as many different things than what I'm showing here. Most of them tend to be rare. These are the things that are very common. Okay, this is the kind of stuff we see every day. We also have cases where we see additional peaks past 28S. We get strange, large entities in here well past 28S, past the 4 kb range. There's all kinds of odd anomalies that you can see in RNA, and you need to be aware of this when you're picking out a method in order to do your library prep for your sequencing, because your results will be very dependent on what you choose at that point. Okay, so now that you've sort of got some RNA quality ideas, what does this look like, the samples that I'm working with, okay, well, in order to pick a method, there's a bunch of questions you have to answer that are related to that. So first, what species is it? Not all the kits that we work with will work with every species, okay? How good is the total RNA? We were just talking about that in the last one. How clean is the RNA? Some methods are a little bit more susceptible to genomic contamination than others. We always recommend DNA-ing the samples. Usually that cleans them up, but sometimes better than others. How much total RNA you have will very much dictate what protocol you're able to use. Okay? Some of these protocols require a very substantial amount of RNA. Some of them can work with very small amounts. And finally, what is it that you want to analyze? Is it messenger RNA? Is it small RNAs like microRNAs? Are there other species in there that you're interested in? These are all things you need to understand and know before you start to do the experiment. Okay, so I'll give you an example. Or I'm going to walk through actually a number of these, and I'm going to show you examples of what you can use a particular prep for versus what you can't. So this first one is a poly-A selection protocol. This probably gives you the cleanest messenger RNA that you can get out of all the different protocols we've utilized at the GIAC over the years. Basically, you're capturing the poly-A RNA. And so as a result, there's a requirement, and that is that this RNA has to be intact, good RNA. Okay? If you've got degraded RNA, this approach does not work. In addition to that, you need 10 to 20 micrograms of total RNA, because most of your RNA is going to be ribosomal. So in order, if you're just selecting out poly-A at the end of the day, you need this much in order to get enough to do your sequencing on. So for poly-A selected RNA, you've got to have high quality RNA, and you have to have quite ample amounts. So for most folks, this really only works for cell culture or some tissue where they've got just abundant amounts of RNA. The most popular approach that we probably get requested to use is ribosomal depletion methods. Okay, so this is a little bit different from poly-A in that instead of pulling down the messenger RNA, what you're trying to do is deplete the other stuff, particularly the ribosomal content, which of course is the majority of what's in there. Okay, these kits, you do have to check and be careful because there are some species compatibility issues with some of them, but it allows you to get messenger RNAs. It also allows you to get non-coding RNAs. It basically will let everything through except for really short stuff, which you size select on, and most of the ribosomal. And I say most because these kits are not perfect at depleting out the ribosomal. Okay, you're going to get some, and I'm going to show you some examples of that at the end. Typically, it's not a lot. Typically, it's on the order of 5, 6, 7%. But you have to be aware that they're not perfect. You're going to get some ribosomal reads at the end of the day. Okay. Once they're depleted, you go through your standard approach and you do your sequencing. This requires about 1 to 5 micrograms. So on the order of about a magnitude less of the poly-A selection approach. So this typically will work with cases where, again, you have sort of ample tissue that you can pull from. It will also work with really any level of quality of RNA. So unlike the poly-A selection, you can really put any sort of level of degraded material into here, and you will get something back. It may not be the greatest, but you'll get something back that's likely usable. So that's why I basically show the 3 different degradation traces over here on the other side. The one thing we do not recommend using this with is anything with substantial genomic contamination, and we'll get into that in just a bit. So what about low input? Okay, so those methods require pretty substantial amounts of RNA. So what happens when you've got 2 nanograms of RNA, not 2 micrograms of RNA? Well, there are a couple of options. Okay, one of the options that we currently use quite a bit is the CloneTech Smarter kit. This allows you to start with anywhere from 1 to 10 nanograms of total RNA. The one thing that you have to watch out for is this does have to be pretty high quality RNA. You can run it with a modest degree of degradation, but you really want intact high quality RNA for this. It can be a very small amount, but you still want it to be high quality or you're not going to get as good as results as you would like. Okay? And for high quality RNA, and I'm going to show you some results of an experiment we did towards the end of the presentation, this probably generates the best results we've seen of any of the approaches in terms of sensitivity to differentials and expression level of the different protocols with intact high quality RNA. So what happens if you have low input and it's degraded? Basically your worst case scenario. You've gone and you've scraped something off of a slide, okay, that's 5 years old. It's very degraded, you have not much material, but you still want to be able to get something out of it. Well, there is actually a kit that works for that. This is the Sigma-seqplex RNA amplification kit. This kit is kind of interesting. We've done a number of tests with it where we compared it with very high quality to CloneTech, and it's not quite as good as CloneTech with the really high quality RNA. However, you can put pretty much the worst RNA you've ever seen in terms of degradation into it, and it looks almost the same as the output that you get from the high quality RNA. It's extremely consistent. Okay? It's not terribly surprising because Sigma had another kit for microarrays for many years called WTA2, which produces results that are very similar on microarrays. It's random primed, and you just get a very consistent result out of it. It's not the best for high-quality RNA, but for modest to low-quality RNA, it actually works very well. And again, you can work with, the inputs are recommended for 1 to 50 nanograms. And again, like the CloneTech, though, we've tested these down into the upper picogram range, and you can get something from them. Up until, what, a year and a half ago, the primary kit we were using for low input was the Nugent Ovation kit. And version 1 of that kit worked very well. Now, it was not really meant for degraded RNA. It was really meant for decent RNA, but in terms of integrity. But it worked pretty well. Version 1 of this worked really well. For some strange reason, when they went to version 2 of the kit, we started to have a lot of problems with this protocol. And we still get people requesting it, but it's really hit or miss, and we don't know why. We don't know if this is a quality issue with NewGen or what the problem is. You can use it, but we really don't recommend it anymore because of the fact that the quality's kind of all over the place with this one. And then for small RNA, and this is something to be aware of, so as I've been going through this, most of these really are designed to pick up messenger RNA. As I mentioned, the ribosomal depletion methods will give you everything but really small RNA at the end of the day. You can get microRNAs from it, but they're going to be the larger, immature microRNAs that haven't been clipped down. And really a broad spectrum of anything of any size other than ribosomal. If you want to look at small RNAs like microRNAs, that requires a separate type of preparation protocol. So this is where some of the things and some of the confusion lies, I think, with RNA-Seq, because folks think that you can go in with RNA-Seq and just sequence everything you want. And that's not actually the case, okay? If you want small species, there's specific protocols for small species. And as a result, you're not going to get the other stuff. If you want the other stuff, you're not going to get the small stuff. So much like what I'm going to show in a little bit later with respect to some of the other things in terms of how you sequence and how you do the analysis, you have to know what you're looking for, and you're not necessarily going to be able to get everything from a single approach with RNA-Seq. So it's just something to be aware of. One of the things about the small RNA prep that we do use is it does require a microgram of total RNA, and you have to have, it has to be pretty good intact, high integrity RNA. Okay, so that's a bit of a flavor, all right? There are other kits out there. Those are the ones that we support in the GTAC. That said, anybody can go out and do their own library prep with a different protocol, different kit, whatever, if they want to in their own lab and submit it for sequencing, whether it's with us or with anybody else, all right? There are other protocols out there. There are some that we've looked at, but these are the ones that we run internally because they seem to fit most of the niches that the folks internally are working with. There are some things like stranded RNA preps and some other things like that that I think we used to run the stranded RNA prep at one time, but we didn't have much call for it, so we've dropped it since. But again, it's something that can be done. This is kind of what RNA-Seq is today, where microarrays were probably 12 to 13 years ago in terms of the maturation of the technology. There are a lot of different preps out there. There are a lot of different informatics tools out there. There are a lot of different ways to look at these data. That's not to scare you away from it and say, don't use RNA-Seq. It's just to say, be aware of what you're getting into when you do RNA-Seq. Know that not one prep is going to give you everything. Okay? Not one protocol can handle every type of input RNA. Okay, so actually before we move on to this next section, I think I was going to just see if there were any questions about sort of each part of the section before I move on to the next one. So are there any questions about the RNA prep before we move on to the sequencing?
Can you explain what the RIN value is that you're citing?
Sure.
Those, and how do you get that?
Okay, so when you basically do like a bioagilent analyzer run on the sample. Oh, sorry. The question for the folks online was what is the RIN number? So that basically stands for RNA integrity. Okay, and it's effectively calculated from those traces that you see. It's a rough estimate of the quality of your RNA, and I say a rough estimate because it's not perfect. Okay, things like a little bit of genomic contamination don't necessarily impact your RIN number the way they should. Those sorts of things where a human being really probably needs to look at it, but the RIN gives you a rough idea. If you come back with a RIN of 8, you've probably at least got some good intact RNA for the most part. Okay, if you come back with a 2, it's probably pretty degraded. Okay, and again, this is something that's calculated and generated as part of that analysis. Any other questions before we go on to the sequencing part of it? Okay, so what about the sequencing? So this is another question we get all the time. How deep do you need to sequence when you're doing RNA-Seq? All right. Well, the typical depth of sequencing that most folks do, and this is really for pragmatic reasons, probably more than anything, but it also has some connection back to microarray. So most of the folks that are running RNA-Seq with us, if they're doing a standard type of run, will put 6 samples in a lane. depending on whether or not you're doing a rapid run or a high output run, that will be anywhere from 25 to 30 million reads per sample. Okay? What that will get you in terms of genes detected on a good run is, there's an example of it down here. So here are the statistics from one of our 1x50 runs where we had 6 samples in a lane. I clipped off the side here. There were actually 6 in the run, but I clipped it off in order to get it to fit. And you can see that the genes detected, based on the analysis approach that was used, is in the ballpark of about 28,000. If you were to take these same samples and put them on a microarray, a good quality RNA, intact, etc., and put them on a microarray, you would pick up about 28,000 unique probes on a microarray. So basically what I'm saying is that 6 in a lane will get you something, if it's a good run, if your libraries were good, you've got good on target, good map back, you're going to get something that's about equivalent to a microarray with 6 in a lane in terms of the things that you're detecting as being expressed in that sample. Okay? Now, I say roughly because the exact apples-to-apples comparison is actually very difficult to do, because a probe on a microarray picks up multiple transcripts and so on and so forth. But this is an approximation. And then you can see a little further down that there's this thing called CPM, which is counts per million. Okay, this is basically a number of counts for that particular gene. So if it says 10,000, that means 10,000 of the genes that were detected had at least 5 counts per million. All right. So, and then 4,300 have 50 counts per million, and about 2,300 have 2,400 of about 100 counts per million in this particular run. This is a fairly typical run, and again, this gives you data that are fairly similar to what a microarray would spit out for the same scenario. This graph over on the lower right is what I was referring to in terms of your ribosomal fraction. All right. Really, none of the methods that I mentioned are perfect in completely removing the poly-A selection is probably the best, but none of them are really perfect in removing 100% of the ribosomal reads. You're going to get a little bit of ribosomal in there. Ribosomal depletion, oddly enough, is probably the worst. Okay, you're going to get more ribosomal reads from a ribosomal depletion than you will really from most of the other approaches in general. And what you can see over here is what I plotted out in this lower right corner is the, can't really see my mouse in here. There we go. Is the last 6 months or so, so I took several hundred runs that we had generated data for, and I plotted out the percentile, or the percent of ribosomal reads. So the median value in terms of what we get back for ribosomal fraction is about 5 to 6% on about the last 700 runs that we did. Okay, so you can see that most of your samples, most of the samples that we do, especially with like the clone tech or the amplification protocols, are going to give you something where the ribosomals are about 5 or 6%. Even the ribosomal depletion will tend to be under 10%. Right? Now, why that's important, though, is that if you have something where you're getting a much higher percentage of that, you're going to need to sequence deeper to get values that look like this over here on the left. Right? That's why it's important how much of this is ribosomal. You don't, unless you're doing something that most people don't do, you don't care about the ribosomal reads in this sample. Those are basically just taking up the good reads of your messenger RNA or whatever it is that you're really looking for. So that's why it's sort of important to know what your ribosomal fraction is and whether or not that's really impacting your analysis at the end of the day. Okay, so 2 of the other questions that we get all the time with respect to sequencing is, should I do single in 50 base pair reads or should I do paired in 101? All right. As if anybody in here has done any sequencing, they know that paired in is quite a bit more expensive than the single in 50 runs. Really, no matter where you go, get it done. They're more expensive with us. They're more expensive really anywhere else. Okay. So what's the advantage of ever doing a 2x101 with RNA-Seq? Well, in terms of looking at the just general expression data, there really is no advantage with 2x101. So what I have down here at the bottom is a graph which shows this is just one sample, and frankly, this is the worst one. Most of them are much tighter than this. We took the same sample, we prepped it the same way, except once we prepped it for single N50 reads, and the other time we prepped it for paired N101. Okay, we ran them, we sequenced them, and then we compared them to each other. And what you can see is it gives you a very tight distribution back. I mean, these are two completely different sequencing runs, and other than a handful of genes that fall off of that center line, I mean, like maybe a dozen, and then of course you got a little bit of spread down here at the very low end where things can be a little bit noisy anyway. But this looks really not much different than if you did two 1x50 runs, all right? And I can tell you that this was the worst one that I picked here. We ran multiple samples, and many of them were much tighter than this. So in terms of just overall expression, 2x101 doesn't really get you much. Where 2x101 comes into play is for people that are looking for isoform differences, especially if they're looking to identify novel isoforms, because the longer reads are really critical in identifying the different isoforms and how those reads map back to those different isoforms. So if you really have an interest in isoform differences, really beyond just differences in expression of known isoforms, if you're looking for new isoforms or isoforms that are not well characterized, that's where paired N101 can really come into play and really help you out. But it's at pretty significant increased expense. Okay? So it has to be something that you're really interested in. In terms of replication, this is where it's definitely a little bit different than microarray. So just so you folks know, I've been here for 3 years now at WashU, but before that I was at Pfizer for 14 years. And the legacy organizations they absorbed over that period of time, which is a long list, I won't go through that. With microarrays, we hardly ever ran a microarray experiment where we didn't do a technical replicate on every sample that we ran. Okay, it's just the way we did it. We wanted very high sensitivity. We wanted very, very good ability to detect even low changes in expressors. For microarrays, technical replicates are never a bad idea. With RNA-Seq, for a couple of different reasons, including the analysis approaches that are out there, it is really critical to increase the number of biological replicates that you run. Most of the differential calculations that are done with the packages that are available are completely dependent on biological replicates. So if you've got the ability to run more samples through, don't spend it on technical replicates with this technology, spend it on more biological replicates. Okay, and you're going to see that highlighted in a few of the analysis techniques down the road. Okay, so what about the analysis itself? Well, this is also where it differs a little bit from microarray, because there's a number of different levels that you can do the analysis on. You can do it at a gene level, you can do it at an exon level, you can do it at a transcript level. All right, I'll be honest with you, for the most part, we have our pipeline set up to really generate any and all of this. Because some folks want to look at the data at a gene level, some want to look at it at a transcript level, some really want to get down to the exon level and look at specific exons, especially if you're looking at isoform differences, that can be critical. So the pipelines that we have set up, as you'll see in a minute, really are designed to generate all of these data. The isoforms that you get are generated a couple of different ways. Well, okay, so they're really generated mainly one way now. RNA-Seq data is first mapped back to the transcriptome of the species that you're looking at, assuming that there's a transcriptome available. Okay, so if you're looking at human data, for example, it's going to go back against the basically ensemble version of REF-Seq. All right. Anything that can't be mapped there then goes against the genomic reference. And this is how it tends to find things like different isoforms, novel isoforms, that sort of thing. Because obviously if you've got an isoform that's not in REF-Seq, your read's not going to map. So it's going to take it over to over to your genomic reference. And what it often does is it will take the reads that you have, and this is where, if you're really interested in isoforms, the paired N101 is sort of key. It will even take those, because of the fact that you can be crossing exon junctions, right, which in the RNA, which is difficult to map back if you're mapping back to genomic, is the tools will take those 100 base pair reads and break them down into smaller fragments and attempt to map those across exon boundaries. Okay? So there's a fair bit that goes on in the analysis of these. And then really probably the most complicated thing that we're working on right now is allelic expression. I'm not going to talk too much about that today, but that's something where you really need both your RNA-Seq and a genomic reference of some sort that you've sequenced in order to do those work accurately and consistently.
Quick question.
Sure.
Could you distinguish between a gene and a transcript?
Sure. So the difference between a gene and transcript is simple. As we know, a gene basically is, based on how the gene has been defined, a total number of exons within some boundary. Okay. Transcripts specifically may only pull certain exons from that particular gene. So, for example, and this is the average number of transcripts that exist, at least the last estimate that I saw, the average number of known transcripts for any given gene in the human genome is about 4 to 6, meaning that each one of your genes can make about 4 to 6 on average. Some of them make 1 or 2, some of them can make 30 or 40, okay? But on average, there are about 4 to 6 different transcripts that can be made from that one gene. All right, and so that's why there's a difference there between in fact, the tools are different to generate transcript level data versus gene level data. And in fact, that's why this is actual GTAC's actual pipeline for doing our bioinformatic analysis for anything that we run. So if anybody who's used GTAC, and this is not a plug for GTAC, but as you know, we will do what we call Tier 1 bioinformatics. So if anybody runs RNA-Seq data with us, we will actually run your data through this pipeline to generate the exon level and gene level data by default, and we can also generate the transcript level data if it's requested. Okay, and we don't charge for that. That just comes along with your data. But effectively, it all pretty much goes through a tool initially called Top Hat, where it uses an aligner called Bowtie to do the alignments. And then once you have the alignment data, we can actually send it through 3 different tools. One which is RCQC, which is sort of a quality check, but it also calculates RPKM data, which is, you'll see this in the literature, RPKM and FPKM. So reads per kilobase, read per kilobase exon per million reads, okay? Or fragments per. So that's the difference between RPKM and FPKM, if anybody's ever seen that and been confused. And basically what that means is it's sort of a normalized version of your count data based on the length of the transcript and or gene that you're looking at. All right? Reads is basically for single end, fragments is for paired end. That's the only difference in the nomenclature. But in addition to that, EdgeR and GIAC, which are the 2 tools that we have for the gene expression and exon level expression data, can also calculate your differential expression data. Okay? These are tools where biological replication is critical. They tend to be very restrictive. So I think I'm going to pass on this one. These are the main 2 tools that will generate the data that we spit out. And as Eric Tixon, who's sitting in the back, who set up these pipelines for us in the GTAC, will tell you, these tools tend to be very, very conservative in calling a differential expression. All right? So the more biological replicates you have, the better off you're going to be, and the more likely you're going to get a substantial number of differentials back at the end of the day. If you've got a very small number of biological replicates, by default, you're probably going to get back a very small number of differences, what it calls significant differences, because of how strict these things are in calling those. All right? Now, that doesn't mean you have to use these tools to do that. We will generate those data. We'll send them to you as part of what we do. But you can take these data yourself and actually determine whether you think they're differentials or not using other tests. Okay, that's what these tools are. The way they're designed to work, they're just very, very restrictive in terms of what they call. So now what I want to do is I want to go. I don't want to go too deep into that because again, we're going to have another discussion about that, and we can spend really an hour just going through the nitty-gritty detail of those analytical approaches. All right, that's really another discussion that we're going to have. Probably the biggest question people have is, should I be using microarrays or should I be using RNA-Seq? And what I'm going to tell you is that it frankly depends on what you're trying to get out of your data set, and it depends on what it is that you're doing. If you're trying to get the best possible data, again, it's going to be context dependent. If you're writing a grant, I'm going to tell you right now, put RNA-Seq in there, because we've heard one story after another about people being told, or people getting dinged or hammered on their grant proposals because they put microarray in instead of RNA-Seq, because RNA-Seq is the hot thing out there. All right. What I'm going to show you, though, are data that basically tell you that it's not that simple. All right. So this is an experiment that we ran in the GTAC, and these aren't the only data that we have that support what I'm going to show you, but this gives you a very nice overview of what this looks like. So we had a set of samples where we took a human, this is the Agilent universal RNA. So basically they take RNA from a number of different sources, tissue types, cell types, etc., and they pool this into this universal RNA. So if you will, it's sort of an averaged human RNA profile. Okay, so virtually everything is expressed in it to some degree, not always high, but to some degree. We also took human bone marrow, which of course is going to be high in hematopoietic cells and is going to express the things very highly that are in those cell types, but not so much in a lot of the other cell types in the universal. So you're going to have genes that are very, very different between these two RNAs. We then diluted the Agilent universal into the bone marrow. Okay, so we did basically 1 in 4, 1 in 16, and 1 in 64. And so what you'll see, that one of the reasons that we did this as close as we did is we wanted to see the ability of the platforms, not just to see big differences, but we wanted to see the ability of the platforms to be able to reproduce what are really very small changes here. This is 25%, this is whatever that is, 13%, and then this is like a couple of percent, right? Not even a couple of percent. So you're really going from within a pretty tight range here within this particular set. And we took this across 5 different platforms. We took it against the AFI HTA 2.0 platform, which is their newest whole exome array, the Illumina HT12, which is the low-cost, most popular platform that we run, the Agilent 4x44K, which, as you'll see in a minute, is the most sensitive platform that we run, the Clone Tech, and the Ribo Zero for 2 completely different types of approaches. So we had a amplification-based approach, and we had a ribosomal depletion approach. Since the RNA wasn't an issue, we wanted to really test the spectrum here. Right? The results were kind of surprising, to the point where this was work that's done by Jinxing Yu from our group, and he actually is we're going to be publishing this, so I'm only going to show you little tidbits of the data here until we get the paper out. But you can see the main take-homes from it. All right? So the first thing that we had to do is we had to figure out what we could compare apples to apples. This is another issue people have when they look at these types of papers. I have not seen, I think, but maybe one paper ever that did what I would call an apples-to-apples comparison between these platforms. All right? What happens is they go find things that map to a common REF-seq ID, and then they go compare them. All right? Well, I can have a probe on a microarray that maps to that REF-seq ID, and I can have RNA-Seq data that's from that REF-seq ID as well, but those same data might map to another REF-seq ID, all right? Because if you've got different isoforms, it's very likely these things can map to different transcript sets. And so most of the analyses you're ever going to see do not do this in an apples-to-apples way. So we actually did a true apples-to-apples comparison. Jen Chang and Paul Clifton and the bioinformatics group in GTAC went back and they identified probes from the arrays as well as transcript sets from the RNA-Seq that were effectively identical, meaning that this probe off of this microarray matches the exact same set of transcripts that the probe from the other microarray matches, that the probe from the other microarray matches, that the RNA-Seq matched up to at the exon level. Okay? So we had an actual apples-to-apples comparison. Out of all the stuff across the platforms, there were a little over 9,000 transcript sets that we were able to identify data for that allow us to do this apples to apples, right? And we also did this at an individual gene level to see that this wasn't, and with Pac-Man data to make sure that we weren't fooling ourselves. And what you can see from this graph on the lower left is that there is a wide range in terms of the sensitivity of these platforms in detecting differentials. So the Agilent 4, let me tell you what this bar actually indicates. What this means is if I take those 9,000 genes and I calculate the differential expression, some of them may not be different, some of them will be different a little, some of them will be different a lot. But if I take those differentials and calculate them on that platform, compare them to the other 4 platforms, on average, the Agilent platform showed an 80% greater difference in the differential than the other 4 platforms. Okay? Now, that's on average. If you look, you'll see that the Illumina was about 40% greater on average because it was smaller than the Agilent, but it was greater than the other 3, including the 2 RNA-Seq platforms. All right? And actually, what happens if you look at the Agilent versus the Affy or the Ribo 0, it's almost 200% greater in terms of the differentials that were detected than those 2 platforms on the same transcript sets. All right? This is an example of an individual gene. Unfortunately, I goofed. I don't have the TACMan data on here, but what I'll tell you is that the TACMan data virtually sat on top of these 2 lines, the Agilent and the Illumina. Okay, they were almost spot on with the TACMan data. We had 10 genes that we already had TACMan data for from these samples, and the TACMan data showed us exactly what we saw with these 9,000 genes. Okay, the fidelity to reproduce the differential for those 2 platforms was far greater than the other 3. CloneTech was the best of the 2 RNA-Seq platforms that we got. As you can see here, it's sort of in the middle. It's about halfway to the 2 best microarray platforms and about halfway better than the other 2, the 1 microarray and the Ribo 0 platform. But I apologize for the slide switching. We think the Ribo 0 issue has to do with, even in these high-quality RNA samples, we did a very sensitive detection for DNA, a DNA-RNA ratio in the sample. And what we found was that there was an indication that about, what was it, about 5 to 8% roughly was the estimation of that sample still contained DNA, even though these things had been DNA'd. And we believe that the ribosomal depletion method is very, very sensitive to that because of the way that it works. Because what you see is that on the larger differentials, the fidelity is pretty good, but on the smaller ones, on the lower end, it just doesn't pick those up. Okay, it kind of flattens out when it gets down to the bottom. And so we think at the moment that this may be due to even very small amounts of genomic contamination give you low-level compression, low-end compression, I should say. So things that are not high expressors are going to be impacted more than things that are high expressors, obviously. This goes back to that selection process. What are you trying to find? What are the questions that you're trying to answer? All right? That is what's going to dictate what approach you take here. All right, so a few other points. All right, because of time, I was afraid we wouldn't be able to get into too much data, and again, because we're getting the publication ready on this, there were a lot of other data that were collected that we'll hopefully be able to put out there soon. But I do want to give you a bunch of other take-home points from not just this experiment, but a bunch of other comparisons we've done where we've done RNA-Seq and we've done microarray on the same samples. Okay. The 2 microarray platforms I mentioned, the Agilent and the Illumina, and really the Agilent, are by far the most sensitive platforms we have. In fact, the Agilent makes sense because we use a direct label incorporation approach for labeling the RNA, and it's on a scanner that has an extra order of magnitude of sensitivity than most other scanners. Okay, so it kind of makes sense. And in fact, again, one of the other data points we found is if you took all of these data and you took the 2 known starting points for your RNA and the 2 pools, the ability of each platform to reproduce the linear trend across that dilution, Agilent was 70% on target in terms of reproducing that trend line, meaning you didn't have something go up and then come back down and then go back up again. It actually reproduced the trend with great fidelity. The other platforms were about 50%. And that really just comes back to the sensitivity. Of course, as we know, generally speaking, the microarray platforms are not good at detecting isoform differences. You are going to get whatever that microarray has a probe on there for. They tend to be very 3' biased, okay, because they try to work with, assume that the RNA is not always going to be of the highest integrity. And so the manufacturers try to make their probes very 3' biased. You get what's on there. That probe might detect 2 of 6 isoforms. It might detect 4. It might detect 3. You don't know. And you have to go back and look to see what it's actually picking up at the end of the day. They can only detect what they've got spots for. All All right, that is the limitation of the platform. They're not dynamic, so what you see is what you get. And you can do messenger RNA or small RNA, but you can't do them both at the same time. Although, as you've seen, you can't really do them both at the same time with RNA-Seq either. Within the RNA-Seq platforms, Ribo0 definitely has the ability to detect more species of RNA really than any of the other approaches, including the amplification-based approach. But it also tends to have more of a compression effect. We've seen this more than once. The clone tech seems to be the most sensitive with high-quality RNA. Okay, and that's not just the two that we compared here. Of all the platforms we run, I have seen the best data with the clone tech platform with high-quality RNA. All right. Now, one little caveat: we did have an investigator use the clone tech system last summer. And this is the only time we've seen this, and so we think it might be reagent specific because we've never seen it again. We got some sort of weird, what looked like PCR jackpotting effect, where one transcript took up 50% of their reads, and we were not able to reproduce that afterwards. Okay, so it was as far as we know, it was a one-time anomaly. But full disclosure, we do throw that out there. We did see that one weird anomaly that looked like PCR jackpotting, for lack of a better term. We really couldn't explain it. The sigma-seqplex, as I mentioned, is the most consistent. If you have RNA of differing qualities, that is probably the best platform to look at, okay? Because you're going to get pretty consistent results back, because the way it's random primed, you get pretty consistent results back regardless of the integrity of the RNA. All right. So if you're kind of from modest degradation to higher degradation to low degradation, you probably need to look at using a kit like that, because any of the other kits, you're going to get all kinds of artifacts just due to the level of degradation, different levels of degradation in your samples. But of course, the intangible, if you're writing a grant, I cannot tell you how many times we've had researchers come back to us, and really within the last 6 to 9 months, and say, man, we really got dinged. I mean, I had a couple researchers tell us they were convinced that that's why their grant got turned down, is because they said they were going to use microarrays instead of RNA-Seq. Now, it's not saying that that's in every case, but I've heard it happen. And I've heard a lot of people say they're getting dinged for saying that they were using microarrays instead of RNA-Seq. So it's just something to be aware of. It may not be the most sensitive platform for everything you want to do, but if you're writing a grant, it's something that you need to think about. Okay? So given the time, I'm going to stop there, and if there are any questions, feel free to throw them out. If anyone online has a question, if you can type it in the Google chat, it can get recommunicated back up to the front. Yeah.
So the microarray manufacturers have these human chips really dialed in for people with non-human data sets. Does the story change a little bit?
So mouse and rat are also, oh sorry, the question was whether or not that those data really apply to anything other than human. I can tell you that for the mammalian chips that are, so production chips, I would say the data tend to be very similar. So mouse, rat, things where they have a production platform with those vendors, the data tend to be pretty good. When you're doing anything custom, or they've got sort of these offerings for these species that don't get run a lot, especially if there's not good reference genomes to work against those, yeah, those may not be as good. Okay, so that is something to be aware of. If you're doing a species where this isn't some production array system that one of the vendors has and sells a lot of, that is definitely something to be aware of. Yeah.
I was wondering, I feel like my hypothesis right now is that the library prep of RNA-Seq is causing a lot of noise for us, more than other steps may. I wonder if that's what you see, and then also if that, or maybe the analysis techniques may be the reason why microarrays appear to still be more sensitive than RNA-Seq. So
the question was around whether or not library prep is causing a lot of the variation, or at least sort of as an observation, that library prep may be causing a lot of variation within the RNA-Seq methods. And then the second part of the question was about
if that, or maybe the analysis techniques are just not as mature.
If that or the analysis techniques are not being as mature, might be leading to the lack of sensitivity as seen compared to microarray. So absolutely, library prep is critical to getting good data out. But obviously, good RNA quality is too. So I would say the two go hand in hand. And yes, the techniques that are out there today for RNA-Seq absolutely are not as mature as the techniques for microarray. They just aren't. I mean, microarray's been around a lot longer, so those protocols have been refined for many, many years. So yeah, and you know, you can kind of tell from the bioanalyzer products, and your bioanalyzer runs on your products in a lot of cases, really how good or variable the libraries might be. So that's absolutely an issue. Now, the data I showed here are best case scenarios. These libraries look fantastic, and that's as good as it got. So I would say in this particular example that I showed, that was the library prep probably wasn't the case. It was very high quality RNA, very high quality output from the library preps. The analysis techniques also, you're absolutely right. These techniques, in my opinion, are not very mature yet. Again, these are where microarray analytical techniques were 12 years ago, 10 to 12 years ago. So they are still advancing, they're still maturing. It's kind of interesting because when one of them comes out with a really cool paper and shows some new change they made and how it enhanced something they did, all the other tools will all of a sudden grab that and add that in as part of what they do, right? So this constant turnover that you're seeing, absolutely, this technology is still evergreen at this point. It's still advancing, it's still getting better on all levels, everything from the prep through the analysis. Okay, well, I got one down here. Let me take this one first, and we'll go to one from the booth.
When selecting the best method for the RNA-Seq, is it advantageous to collect all your samples, do see what quality your RNA is at, and then choose the method?
Yes, absolutely. So the question was, is it advantageous to collect your samples, get your RNA quality back, and then choose the method? And the answer is absolutely. Because you may think you're going to use a particular approach, and then when you get your RNA back and look at the quality, you may find that that approach isn't applicable on those samples. So absolutely, we definitely recommend getting the samples. I mean, you already know that you're going to do RNA-Seq. You kind of already know how many samples you're going to run, etc. At that point, you're just saying, all right, what is going to give me the best output based on the input quality of these samples? So what was the question from the booth, Seth?
And 50 base pair single NV ever prescribed transcript level data?
Can it provide what? I didn't quite hear that.
And single NV SR50 ever provide transcript level data?
Yeah, so
just a little tiny snapshot of the gene.
Yeah, and so the answer is you can put it through and you can run the analysis and you will get